example is from long, long time ago, like 550 years ago. And I didn't know about it till a few days ago. Apparently, around that time, there was like an evolution Big Bang. Before this time, all the things we have in the world was like very small particles in the sea, right? They'll kind of float around, and if the food comes to them, they'll eat. And they're very passive. Nothing really happening for a long, long time. And all of a sudden, apparently the whole world exploded with animals and stuff like that. What happened? And what they find out, one of this little creature developed an eye. If they have an eye, they can see where the food is, and they can go to the food, right? And then other particles can see them, they say, oh, let me go get them, right? So it's the development of eye in a biological platform, right? Really changed the entire world. If you think of us, we mostly learn by seeing, right? Our 2/3 of the visual cortex or the brain part is really meant for visual processing, right? People have been fascinated by that. Let me show you, let's come back to 1981. Anybody knows this right, you guys? Or maybe not. So they are celebrating. Right? There's Hubel and Wiesel, they are neuroscientists from Harvard, and they just received the Nobel Prize. Why? Well, they have been studying vision for the last 20 years. And specifically, I'm not sure why, cat. Right? So what they did, they take a cat, kind of, don't really kill it, kind of make it sleep, and they stuck an electrode in their brain. Right? So once they stuck the electrode in the brain, then they kind of attach that electrode to some kind of speaker and show it pictures. So what they're trying to hope, by poking around, can you understand how it says? Just like actually our previous speaker was talking about MRI and showing things, very similar 1960 version, right? And what they found, so initially what do you think, what does the cat like? Maybe it like fish. So we showed a fish, the picture of fish, nothing happens. Well, show a mouse. Nothing happens. Right? So they're very puzzled. They're very puzzled. And let me show you the video so you'll hear from their own words what really happened. Let's see. Can we see the browser? How do I make the...
We set up our first experiments, and they didn't go.
Bring it over here. Full screen from the beginning. There you go. Let's turn the volume up. And here's the story from them.
The researchers actually listened in to individual nerve cells firing in the anesthetized cat as they presented it with different visual images.
When we started working, Torsten and I, in the late 50s, we set up our first experiments, and they didn't go well because at the beginning we couldn't make the cells fire at all. We'd shine lights all over the screen, and nothing seemed to work. And rather by accident, one day, we were shining small spots, either white spots or black spots, onto the screen, and we found that the black dot seemed to be working in a way that at first we couldn't understand until we found that it was the process of slipping the piece of glass into the projector, which swept a line.
Let me pause. So what they're saying, they are showing a little dot, right, to the cat. The dot didn't do anything. The dot was in a glass slide. So as they were sliding the glass, the edge of the glass, right, was sliding in the frame in and out. And it was completely surprising. By accident, that's the one that was making the noise. So instead of picking up that blob of circle, the cat was picking up that particular line. So, let's finish it up.
Very faint, precise, narrow line across the retina. And every time we did that, we'd get a response.
So, let's go back to the presentation. there you go. So what they found, let me explain again. So we have the cat, they poked the electrode, and then what they found out is really the cat was responding to only to a straight line. And not only the straight line, the orientation mattered. So it didn't respond to a horizontal line, right? It only responded to the vertical lines. So for the next 25 years, they kept on poking the cat in different areas, right? And they have published a paper and they talk about simple and complex cells. What they found right from your eye, the very early stage, when they poke at those areas, it only responds to simple structures like line, things like that, right? And these neurons, they connect and they make what they call complex cells. They respond to much more complex areas. So it's almost like this, right? These guys see the straight line, these guys see a straight line, they like vertical line, and this guy can see the box. Right? So they continued, like the neuroscience people. Let me show you a recent picture from a French guy called Simon Thorpe, and he is experimenting with monkeys. Right? So that's the monkey hand, monkey eye. He showed the banana, I put the banana myself. So if you look at them, follow the eye, right? You have the eye, they have something called LGN cells. This looks a very early thing. Right here, what they call the V1 region, right? You see the simple visual forms, edges, lines, things like that. You go to the next layer, the people who like neural layer things, that's what these neurons are connected to the next one. It responds or it learns more complex, maybe 2 lines makes the edge, right? You come here to the V4 area, maybe you look at the whole outline. By the time you come somewhere over here, right, you have a concept of banana. So the summary of everything I've been through is that our visual processing in mammals, cat, monkeys, even humans, is very hierarchical. Right? The first layers of eye, or actually not really the eye, it's after the eye, that's just a photodetector. The neurons learn very simple stuff, and the next layer builds on that one, makes something more complex, and goes on. And by the time it comes, and this is very important, you learn an abstract concept. So you see that hat, right? And then by the time it comes, like think of, if you close your eyes, think what is a cat is. You really cannot describe what a cat is, and that definition will be different to everybody. It's a very abstract concept. And this is actually what Alan was talking about. When you hear a word, when you hear a concept, deep inside your brain, it's just an abstract concept. Like think of me, I know 3 languages, right? I'm from Bangladesh, I went to school in Turkey, so I know Turkish, I know English, right? And when I talk with my parents or my Turkish friends, when I'm trying to talk, I have a thought in my head, right? And then I translate it to my language processing units, right? So even my thoughts, when I express, even when I'm talking right now, but right now it's not prepared speech at all, right? I'm kind of making things up. So my thought came in my head first, and I expressed to you with English language first. So even our thought, our language, everything has this hierarchical structure built in. So this is just to give you a cartoon version of it, because I'm going to use this again and again, right? You see a picture, and initially you just see the parts, like maybe lines, and you may see some complex a little bit. At the very end, you see full picture, but not really the full picture, an abstract version of it. So scientists have been trying to copy these things, right? So, and there's so many people, you cannot give, like in 7 minutes or 10 minutes, I cannot give credit to all of them. So I just picked few of the papers that are popular in the literature, right? There's one, a Japanese guy called Fukushima, he talks about you probably don't, the reason I picked, and it's really copied from his paper, he refers to Google and Weasel, right, the cat guys, and he tried to follow the similar structure Google found inside cat, and see if I can make something out of it. Right? And he tried the hand digits, and he could actually have very good progress, right, and using these kind of structures. Let's jump another 20 years. This is Andrew Ng in Stanford, and his students are looking at this data set called Chaos. It's probably somebody in Japan went to the forest and took a bunch of pictures, right? They say, okay, let's build a mathematical model and feed all these pictures to it and see what the first layer sees. And what they found, it sees, the first layer saw really these kind of lines. It's almost like a cat. So that means, the machine or whatever they created was almost behaving like a cat. Cat visual system, they say, right? And the next layer was the combination of all these things and it looked like this. They didn't stop there. So then what they did, there is a data set called Caltech 101, this is the previous, the old one. They had 101 objects like faces, cars, elephant, chairs. And they gave that mathematical model or computational thing or deep neural network, whatever you call it, doesn't matter. The challenge was, hey, take these things, combine in some way, and see if you can come up with these things, right? So they're trying to teach, can you learn a hierarchical systematic way? And what they found out, so that's what you call their low-level features, that's probably corresponds to in my cartoon something like this. The mid-level feature or the mid-layer was learning something like that. You can almost see noses and eyes, right? And the last layer had something that almost looks like a human form. The same thing was for the car, right? They started with the same elementary lines or abstract, simple shapes. You can see a tire that got formed of all of these things, and at the end, have cars. And I'm going somewhere, right? What we're trying to build, what we call deep learning, is some kind of system that can learn this kind of hierarchical representation, we say. Remember I was talking about ImageNet half an hour ago? Yes, we have 40 million pictures, and the task is to identify them with some kind of computer algorithm. And in 2012, AlexNet was the first one that showed big promise using convolutional neural net. So next year, Matthew, I think he was from NYU, he has his own startup right now. He tried to look at, well, let me look what Alex produced. Let me see inside his 8 layers that we have, and some of them, what's inside these things. And what he found, the elementary layers was something like this, lines, blob of colors, right? Somewhere in the middle had some, you can really express what they are. Some kind of combination of this thing and the network produces this thing. At the high level, you have something like this. You can almost say bird head actually. And then of course you use these things to do your classification. And people who knows their science, so for example, if you do linear regression, well, you give it an input vector, right? So you're doing your custom linear feature. Even if you do support vector matches, random forest doesn't matter. You're creating what data to put. And it's very difficult. And if you look at Kaggle computations, in Kaggle computation, everybody knows all the algorithms, right? And you can get pretty good accuracy, which is using standard algorithms, right? But to be the top ranking Kaggle things, it's all about feature engineering for that thing. And it's the art. And it's difficult, it's not scalable, right? It's the beauty of deep learning everything. You just throw everything to the machine, right? And it designs its own feature that it thinks important. And of course, yes, you need 1 million parameters, you run it for 3-4 weeks. It's extremely computation savvy, this way. But it does the work. And I've given you the example only with image, right? But if you think of other things like text, right? We have characters. Character makes a word. Word makes a word group or a phrase or a clause or a sentence, and you have a story. Right? This thing has a built-in hierarchical representation, right? Same thing with speech. As I'm speaking, I have a frequency, and the speech guy is a way of actually defining phonon, and there's a whole model of it. Again, one thing builds off the other. It turned out, in the last few years, especially since 2012, like before 2012, the speech guys are doing their own feature learning, right? Let's look at this and this. Same thing with our text guys. Now, pretty much everybody in this world is using this kind of deep learning approach because it just works so good. So what I try to share at least, and at least I convince myself what deep learning is really about is designing a system that can learn things in steps. Right? The first time what it learns very elementary things in terms of image lines, right? And then it has a next layer that combines the line, makes up something else. Right? And sometimes they can be long, you're right? There can be 2 layers and there can be all these things. And this is very new. I mean, if you look at, there's a new paper comes every month, literally. There's no book right now, actually. There's one book that just came out. But every month, sometimes every week, something new that comes out, and that changed pretty much the entire thinking. Let me give you one caution first. So I've been talking about, of course, brain, cat. Think of flying versus bird, right? We all know, flying was inspired by bird, right? But the aeroplane doesn't really look like this. Right? It's not an exact copy of a bird. I mean, people tried to do flapping and feather and everything. All these things failed, right? The thing that was really one, the Wright brothers plane really doesn't look like the bird, but it has the same concept of lift, right? And this is our modern, like Boeing Dreamliner looks like that, right? So, what people, and I think it's true as well, although we talk about deep learning is really imitating brain, but think of the example I give in terms of flying, right? We really don't know how the brain works. We have some idea, right? And based on that one, we are making this mathematical model that works. And in terms of maybe where we are, this is maybe the Wright brothers thing. This is the Google net, actually. Right? What holds in the future, we don't know. But it's extremely exciting. I mean, the way I personally believe, like every few hundred years, right, there is a technology come that changes your life. Electricity, steam engine, the computer, internet. This is one of the area we just stumbled into. If you look at Google, I think I can relate to the excitement Alan was talking about when giving a Google example. 4 years ago, Google started the Google Brain project that was led by Andrew, and then Andrew led to Baidu. But Jeff Dean is leading it. And I remember listening a talk. If you look at the number of internal projects within Google using this kind of technology, it's almost like a skyrocketing. They're literally betting their whole company on this kind of techniques that they're hoping to give them edge. I'll stop here right now, but trust me, this field is, I haven't taught anything like convolutional neural net. There's more stuff here, but at least to get your interest going. This is something that really big happened in the last few years. It happened because partly say NVIDIA. They had a GPU, right, that was cost effective and you can run these things. Now Google has their ASIC cluster, you can run it in future. So really, sky is the limit what the world will give us. I'll stop here and take any question you have.
One thing I would like to add on this one, more of a comment actually. The reason why I think it's really going to explode is because Google actually released TensorFlow, right? And they're actually starting to release models on top of it, right? So you could pretty much take like a neural network that was pre-trained to see all these birds and everything. And I've seen presentations where they just take out the last layer and repurpose it for your application. So they literally took that ImageNet, removed the last layer and repurposed it so that it actually detects or classifies, paintings. Because in general, it actually knew how to see. It just had to retrain it. So the reason I'm so excited is because now you can actually repurpose the models that somebody else has already trained. So you're not starting from scratch. Your models are actually there.
And actually, that would be my recommendation. Like, if you start playing it to converge any of them, we are talking about 4 GPU running 2-3 weeks, right? Start with slow, start with somebody what they call module 2. They have in TensorFlow, they have in Piano, they have in Cafe, they have in Tosh. You can literally Google search it and find models somebody build it and take those solutions and start playing with it. But what also, go ahead.
Well, I'm just intrigued, it's a little bit off topic, but it's the reverse of what you're presenting in the hierarchical learning. You talked about how you have this abstract thought in your head and then you translate it into Turkish, English, or any of the hierarchy, you're reversing the process.
Yes.
right? So instead of seeing something and being stimulated,
Yes.
there's a germ of an idea in it, and then you have to project it out in the right context.
Yes.
You have to create the context.
Yes.
Does any of this stuff translate? That's the other half, like
Yes.
Siri.
So I'll tell you, I haven't put it here, I wanted to put it. So I remember a talk by Jeffrey Hinton, right, who is literally to me the way the forefather of everything. I mean, this guy didn't give up. He started this thing for 40 years, and everything that could came from his students, right? He is leading the stuff in Google right now, and this is really what he said. If you look at Google Translate right now, still right now what it does a phrase translation. If I say something in English, they have a dictionary of same phrase in another language, say Bengali, and we'll just do a translation, right? What he said, I want to see if I can say verbatim. They are building systems that when you take input, they transfer that to a thought.
Oh, the thought vector stuff. I know what you're talking about, yeah.
That's a thought vector.
Which is the vector
And
of
now
the
once
vector
you have
spaces.
that, you can reverse it, and you can output in another language.
Yeah, that's the vector of the vector spaces, right?
And they actually have this model on TensorFlow, available, English to a French translator.
Well, I wasn't so much thinking of language translation as I was thinking of projection. So you take any, in other words, you have stimulus and you're classifying it, right? Where the other way around is I have some simple idea and I want to make it bigger in a certain
Absolutely.
sense. That's
Absolutely.
really very different though.
Absolutely.
You want to create the stimulus instead of react to it.
You're absolutely right. If you think of the dreaming thing, what they're doing right now, I had a picture all the way, right? So they'll take care of one of the neurons, right? And try to find out what activated, and they reverse it. And that's why you see all these crazy things. So that was exactly what they're doing it. But I'm with you. So think of, can you design a system where you teach all the math, right? If you look at, because I had a math major, right? So in math, there's only very few things there like absolute, right? They're called axioms. Right? If you have 2 points in geometry, there's only one line that can go through it, right? So if you can take a system and teach the basics axioms that we have and let it free, can it generate new knowledge? That's exactly, absolutely right.
Well, that's essentially what AlphaGo was. That's essentially what AlphaGo did.
You're absolutely right. AlphaGo, so if you look at AlphaGo, it's a deep reinforcement learning. What is it? So it's a system that, if you are familiar with corporate culture, it's like a carrot and stick way of running things. If an employee does good, you give it a carrot, right? If he does bad, you beat it up.
I'm gonna watch that with Jeeves.
But anyways, so that reinforcement algorithm more or less works like that, right? You have an algorithm, let it do something, it does something, and you look at what it does, and you have a function called a reward function, you reward it or you take points out of it. So there's only one part of it, is a reward function. For the policy network, it's finding what it is, that's what they use. And this is, remember at beginning of my talk, that literally rang the bell in my mind. That was big. Because now we can design a stock trading program, for example. Right? You buy a stock, you see the response and everything. Actually, if you go all the big conferences for these guys are NIPS, ICML, and I think recently they started ICLR. I heard that if you go there any of this conference, and of course there's Google's and Amazon's trying to hire you. 50% of the people who are trying to hire those students come from financial industry who are designing for stock trading systems. As a matter of fact, actually, I'm going to ICML this June. I already get an invite from one of these sponsor guys. Hey, very interesting job. So there are huge applications of think of self-driving car, right? The one that the guy from NVIDIA, CEO, we demoed in actually last conference. It was an end-to-end system running deep network. So you're talking about self-driving cars. We'll be using some part of these networks, maybe in addition to something else as well. So the sky is the limit. I mean, we just started with image, text, but it can be used with so many other things that we haven't even thought of. Anything else?
Scott, did you have any, so the other sponsor that we have is IntelliJ. Does anyone here owe a license for IntelliJ? I think there's still one person in our group that never got it, so it's